So hello everyone from my side. My name is Ciprian Popa, and today, together with my colleague Tak Shaban, we're going to present this workflow. We entitled the webinar Elevating Structural Engineering with Open BIM. And our main purpose is to show a clear Open BIM workflow using Allplan solutions. And in order to make a logic similar to the way we work as structural engineers, everything will be shown on a project in which I took part. It's a project in Oradea City. It's an art gallery, as you can see in the background. So my name is Ciprian Popa. I'm a structural engineer from Romania. I'm the founder of Structural Glass Design, the company that develops and maintains the structural glass add-on for SCIA Engineer. And together with my colleague, Tak Shaban, he is the customer service team leader at SCIA. You know him from many webinars. We're going to present today the workflow. So this slide is also like a placeholder for our agenda. So these are the steps when working with the Allplan solutions. So one first step is the data collection, which is vital to pick up data from the different stakeholders. So we want to have the data inside our platform. And then there's the structural concept where we, using our experience and engineering judgment, we try to figure out a structure that meets our expectations. So it's a proposal that can be inserted in the data collected. Structural analysis where we get results from finite element analysis. And here we can make some optimizations, some improvements, and check if our expectations can also be confirmed by this numeric model. Structural optimization is a step we'll go through. And then, of course, the deliverables, which are still execution drawings. I will show also other ways of delivering BIM data through common data environment. But then again, in many countries, including Romania, the execution drawing is something vital that needs to be signed, stamped, and this is what is stored and shown during commissioning. And of course, project management, which is just taking the data into the common data environment and use it throughout the execution of the project, but also can be exploited afterwards. So we'll jump directly to this data collection, which is the importing of existing terrain data and architectural theme. So one key feature of this approach is this interoperability of Allplan, which enables to import data from various formats. You see here traditional 2D formats such as DWG, DXF, and also Revit files, IFC, 3D PDFs, SketchUp, Rhino, XML. So many formats can be imported in Allplan as BIM authoring tool and platform. So we can grab the information in whatever system it has been worked, because talking about Open BIM and open platform, we cannot impose something that has been worked by other offices to work in the same approach. So this is one key thing I want to point out here, that this initial data can be point files, vector files, which have this CAD data, pixel-based, so even scanned plans can be imported in Allplan. And then we need to gather this within this platform. So Allplan can be this initial step. Every project starts with Allplan, as I mentioned above, meaning that we can centralize all the data that we have, 2D and 3D on the project, before we even start doing something. And this data can be organized in a building structure, which is ISO 19350 BIM compliant. So let's see exactly the steps and how it began. So this project actually began with a contest. So it was a contest by municipality, and later this project was also nominated the SCIA contest. So it was a contest because the initial theme presented by the architects and approved by a council of architects was not on the citizens' taste. So they didn't want the initial project, so they asked for a redesign. And this was a project awarded by the public. So it started through a contest. It was an underground parking, and on top they wanted to make this art gallery to be symbolic on this Art Nouveau themed city. So this was how it all started, with a project that has been won, an architectural project. And here is the concept from the architect. So on the top side, we can see here the 2D data that was describing the existing parking. So this art gallery that you can see on the second picture below was supposed to be built on top of an underground parking. So we had the 2D data from the underground parking, you see here, format plan from DWG, and on top we got from the artist, because in here there was also an artist, an interior designer, and a creative artist aside from the architect, who made the concept. So this concept, many artists and many architects like to work in SketchUp. It's a easy to use tool. So the data was mostly 3D surfaces. This is what we got from SketchUp. And from structural existing infrastructure point of view, the data that we received was 2D formwork. So this is how we started, and we can see how we import such data. So we have the options to import directly a SketchUp file, and this is a great advantage because the SketchUp file, as you can see here, has also textures, has colors, so it's easy to identify in Allplan exactly what the artist meant. So even details like seeing the drawings, seeing the art itself is visible within Allplan, and the import is straight away. It's just a drag and drop option. Another idea was to use 3D laser scanning, so we can have a cloud point file, so we can get from the laser scanning the data, or more traditionally we can have some DWGs, 2D or 3D, and we can import this data. And the way we import data is quite straightforward. We all just need to calibrate the drawing unit with the practical unit that we want to work in Allplan, and all data is vector, it contains layer, so you basically don't use any data that the initial used it. And it's very important to work like this because there's a ton of data that you can see, and you need to isolate sometimes what is structural and non-structural. So this is one key aspect before starting the work itself. And now there's the structural concept. So the structural concept means that we need to provide some engineering to the work. So we have something existing, we have a theme from the architect, and now we start to, it's our job to prepare a concept, because we as engineers have some experience, have some expectations. So just looking at what the architect wanted, we can include, decide where the flow of force, how the flow of forces can occur, where to position columns without affecting the architecture, and so on. So before actually calculating something, it's very easy to grab everything. So raise in 3D the infrastructure that I shown that was initially drafted in 2D. And then afterwards, we can have the architect, let's say, volume and surfaces which guide us, or what are the obstacles and where we need to position structural elements without having any collisions. And the tool for this is Allplan. So in Allplan, basically we remodel some of the items. Although we have everything looking good, behind we might not have BIM objects. So we might not have IFC native data, which contains attributes such as material, numbering, role, and so on. So that kind of data is relevant to be modeled in a BIM authoring tool such as Allplan. So let's see exactly how this works. So there are different modules in Allplan. It might be a custom with. So we have dedicated, let's say, architectural, but it's also used by structural engineers. So dedicated elements which are recognized by other IFC software. So a column is a column in any kind of other IFC certified software. And we have different ways in layering the data. So we have drawing files, we can use different layers or filters to see exactly what was built. And also we can use parametric data. There are many parametric objects like the grid system, which is also IFC compliant, meaning that you can transfer within IFC models. And we all know the grid system is vital for alignment and for correlations. And of course, we can import the data even from PDF if we have scanned documents, or the architect just provided a nice PDF but could not provide us DW. That's no limitation. And now, if we just draft the position of columns, as I mentioned, we have tools for this. We have databases of profile. Actually, Allplan shares the Nemetschek profile catalog from SCIA. And you can position exactly from the different cross sections that are realistic from a database. We can even merge some details, so we can include a base plate, some anchorage without making any calculations. So just to think of how much the infrastructure elements should be. Would I have place enough to position 4 bolts? So it's just engineering judgment at this point. But having parametric data means that we don't waste time with 3D modeling. But instead, we start to think in 3D. So you see, it's a hybrid mode of working. We work with multiple windows at the same time, and we can focus on the details that matter. And this multi-window approach is actually something that we can position on multiple screens, monitors. So it's a very precise way of working and focusing on the single source of truth. So whenever it's more relevant work in an elevation, or we want to see isometrically, you see that it's seamless, this interaction with the object. So this is why it's very easy to start to make some decision based on the existing input. You see, we're not thinking of any kind of coordinates. We're just trying to stay within the volume of the architecture and respect the existing infrastructure. And step by step, we can make a proposal of the steel structure as we would expect, making sure that in this case, the columns, one condition were to be hidden by plasterboard non-structural walls. So the walls which support the paintings actually also hide the structural columns, because the idea was not to insert an ugly looking structure, a steel elements or something industrial looking like in this Art Nouveau city center. So in order to maintain the beauty of the old buildings, it was needed something to be there but look modern, but not to make any kind of problems. So now we jump to the structural analysis part, and I will just make a quick intro, and Tarek will explain exactly the step-by-step the process. So the idea with this BIM from computer-aided engineering conversion is very important, and it's quite open. So everything I show you, although is within the Nemetschek portfolio with a focus on Allplan solution, any step of the way you can also insert from other platforms. So IFC is a neutral file. So someone who works with an IFC compliant software can jump here and have the same advantages. So it's seamless to export the model from Allplan to AutoConverter, and in AutoConverter you have this conversion. So we take a structural model and we convert into analysis model using different recognition tools, alignment tools, as Tarek will show you in a few moments. So this is a key thing that we can do. So we take from the drawing that was just a bit of guesswork, we provide structural analysis, and the results will be a SAF file. I will now introduce Tarek to present his part.
And now we're going to show the workflow in the platform BIMPlus, and more specifically in AutoConverter, which can transform the structural model coming from the IFC file into an analytical model that we can export later on and run an analysis on any structural design software, and more specifically SCIA Engineer in our case. So here you can see the IFC project which was imported, and you can see on the right side that you have the different types of objects building objects, steel design, reinforcement, and general objects. So we can also in here deactivate the type of objects that we do not need. And you can see that we have the concrete elements, the steel ones, and the glass elements too. So now I will switch to AutoConverter, which is also based on the BIMPlus platform. And here you can see that we can have the same project in it. We have the same type of interface, but here we have different workflows. So actually, you can also consider the different types of objects. We can again deactivate steel design, general objects, and reinforcement. And we can go in the Clean Model tab. And here we will have more detailed objects. You will have the beams, the walls, the plates, columns, the slabs, the members, and the grid. And for example, we can deactivate the grid here. And if we switch, we can see what has been also removed. So I can also remove, for example, the plates. And if I switch again, you can see in here that it was removed from the model. We can also use a filter. So for example, I had already used a filter called cleaned model. And in here, I only keep the objects which are necessary for the analysis. In the next tab, you will have the categorization of the elements more specifically, again, the beams, plates, walls, etc. And here I have created a specific group for the glass beams, for example. You can also have the classification of the cross sections. You can see that we have, for example, IP 200, 270, which were detected automatically. For this one, which the name is a bit different than our catalog, you can go in here and you can choose the appropriate cross section among the different categories of predefined cross sections. And furthermore, you can see that for the ones which are more general, AutoConverter will detect the dimensions and it will create the cross-section automatically. For the materials, we also have a recognition of the classical materials like C25, 30, 30, 30, 57, the steel, for example. And you can also go in the library and choose in here the steel grade that you would need. In the next step, we will transform the structural model into an analytical one. You can see that it transforms the plates into purple surface elements, and you have the beams and columns in brown and the nodes in black. If you select a node, you'll get the information about it, like its location, for example. For a plate, you would get the thickness of the plate, its material, etc. You can also see that it detects small 2D members that we can delete. So the criteria for deleting these elements can be chosen also manually, of course. And here in the alignment settings, you can see the local coordinate system of each beam. And by default, all beams go through their center. But for example, for the beams here, I have chosen to make them go through the top. So you can see that the analytical model goes through the upper surface of the cross section. And then in the alignment settings here, you can have a sequential alignment or one alignment for the whole structure. And the sequential alignment allows you to have a possibility to have a different group of elements being aligned at each step. And for each step, you can choose a different configuration. For example, what is maximum node movement admissible to connect two neighboring nodes? What is the automatic extension? Is it possible or not? And it means here that you can connect a member at a interval of another member and create an internal node in this case. By default, it's 25% of the length of the member. You can also deactivate the automatic extension and specify a specific value in meters in here. And so here I will run the sequence analysis. So now I have a model which is aligned. Initially, we can see both models at the same time, the original one and the aligned one, and I can deactivate it. And now you can see that you have one node connecting these four members, and you can see in the neighboring area, you also have a good good alignment and connection of the members. And we can go also further away, and you can see that the plates are also connected. And now what we can do is either saving the model in BIMPlus to come and see it later on, or exporting it into SEF format. So let's give it a name, aligned model. I will save it. I will open this model. And you will see in this Excel file that you will have a tab per type of information. So you have the SEF version, the national code used, the metric or imperial system. In the material tab, you have the list of all the materials used with their properties. You have the cross section. So you can have a parametric cross section like a rectangular one, or a manufactured cross section, which would be, for example, an IPE 270. You have the tab for the nodes with their coordinate and a specific ID. So this unique ID lets you update the model later on if you need to. So for example, you can come and change the values of coordinate Z and update the model in SCIA Engineer. So even if you had put your supports, you had put your loads, you would not have to create a new model. You just update it, and all the other data will follow also. And then you will go to the structural curve member. Here you can see the beams and the columns. So you can see the type of the 1D member, the node, and the cross section being used in that case. Then you have the edges, which are the internal lines connecting the plates and the walls, for example. The surface members, which are the plates or the walls with their materials, their thickness, and the nodes that will create the contour of the plate. And then you have the openings, which are also considered, and the subregions. So you can have a subregion where, for example, this thickness of the slab would be different than the rest of its original surface. So this model can then be imported in SCIA Engineer, and I will show you how to do it. So here in SCIA, we'll go and open from, choose SEF model. We open the align model. We click on OK. So here you will see the model. I can, of course, show the shapes with volumes, surfaces, etc. I can go and check the list of cross sections which were imported, the rectangles, the hollow cross section, the IPEs, etc. And now we can delve more into SCIA Engineer, the next steps during this webinar.
Thank you, Todd. And we'll continue. I'll continue now. So it's the structural optimization part to ensure safe and economic design according to codes. And here is a key feature of SCIA Engineer, the fact that it has probably the best Eurocode integration. And also it includes even more than the Eurocode. There are also US standards and also other European standards, in this case, the structural glass standard. And the idea is that we can see exactly what resources we have and what is the utilization of each structural member. So this is how we can make economy. So we can decide to limit somehow the number of cross sections, but at the same time we can see if an element is over designed, under designed, and if it's worth if there are any resources left to make some economy in case we have this value engineering or have some pressure for contractor. So this doesn't limit to what you see here. It's available, the integrated design for steel, reinforced concrete, precast concrete, aluminum, timber, masonry, and structural glass. So let's see exactly how it works. So once we got the aligned model from the SAP file, we can now assign some supports and we can run quickly a self-weight analysis. So we can control this support. So on each degree of freedom, on each of the 6 degree of freedom to be rigid, flexible, or have a low non-linear behavior and so on. So we'll run now the analysis and make a check from self-weight to see how it looks. So to make sure that we don't have any kind of singularities mechanism, to make sure that the model that we imported from the automatic alignment actually works. And the next step is we insert panels. So we cover the structural members with panels. And these panels don't have any kind of stiffness, but they just redirect and calculate the tributary area for each 1D member, so it transfers correctly as we would expect. So one quick example is not to load the roof bracings with gravitational loads. So aside from the self-weight, we don't want to position snow on this bracing. This bracing should look on the automatic 3D wind generated data. As you can see here, SCIA has this 3D wind generator which calculates the pressure coefficients on the surfaces, and it even displays quite clearly the peak pressures and their distribution. So it may look complex because it is. The design of wind according to Eurocode is quite complex, especially if we have stranger geometries. Also, seismic analysis can be performed according to Eurocode 8, or we can have other codes. We actually have the Romanian spectrum modeled here, so you just position the site and the behavior factor, but there's also open to other standards. And last but not least, there's the manual input, so even from Excel, any kind of response spectrum can be imported, so there's no code limitation to our designs. So in this way, we ensured everything because Romania is a seismic area, and we wanted to understand the whole behavior of the structure. So wanted to get the real stiffness of the steel connected to the glass and connected to a concrete infrastructure that is positioned on top of something existing. So this is the reason why this 3D global analysis was a must in this project. So going a bit further, there's also more advanced approaches for analysis. We can use nonlinear analysis, for instance, to determine that some members will work only under tension and not on compression. So we have these cables, roof tensors on the roof, which normally should only work under tension. We see here the results from a linear analysis. So from linear analysis, they get loaded also with compression, but we know that with this, they will buckle. So if we want to impose a special behavior like tension only, we have this possibility. And the advantage is not only a reduction in the force or a doubling of the forces and not seeing compression, but we also understand the structural behavior, because if a bracing gets loaded with twice the force, let's say that because the compressed one will buckle, we'll get an understanding of what happens to the joint and the entire structure downwards towards the foundation. So we see here a quick nonlinear analysis, which redistributes the forces so that we only have tension in the members. So we can now look at the nonlinear combination that was the one that would have designed the bracings. And if we look here, there's no more red because we don't have any compressed members. The values are higher, they're not exactly 2 times higher, but they're of course bigger. So there's also some winning here, aside from the conservative approach of just doubling the tension to take into account the buckling of the compressed bracing. Now going onward, we'll focus on the steel structure. As I said, it's a hidden steel structure, and it's hidden within some walls which are placed non-symmetrically. So each frame is unique here. So we can instantly make a structural check of steel. So we see the unity check, which is the worst combination or worst checks between section check and stability check. We have all formulas. We can, as users, we can decide what is the level of detail that we actually require to see our formula substitution or table-like data. And this brings a lot of confidence from a checker or a third party or a consultant, because we can prove the check of each members, and we don't need to guesswork which is the worst member and why we should decide that. We only design that and check that. Same goes for SLS. We can make SLS establish the limits for variable loads, for permanent loads, and we have instant check with the relative displacement on the members compared to an allowable limit. And we see graphical and tabled the data, and same they will go in the report. Now advancing a bit with the connection, because steel is also relevant, steel design comes also with connection. We have multiple possibilities. We have integrated connection design in SCIA Engineer with the component-based method. So whatever is mentioned in Eurocode 3 part 8, we have here. So not only that it graphically models the connection, it also calculates the stiffness of the connection, and we can take into account if we want the stiffness to have redistribution, especially for flexible nodes. So aside from checking the strength of a connection, it also checks the stiffness if we manage to make a fixed joint, or it's hinged joint, or if it's somewhere in between. We have the possibility of checking, and also the report is quite exhaustive, as the method from Eurocode is quite exhaustive. So for typical connections that are described in Eurocode with this method, SCIA just has a module integrated. If we have some situations which are outside of SCIA, then FRILO is another application that can be used to design further connections. So if there are some connections that we're unable to do in SCIA, we use SCIA to export forces via Excel with the forces in a joint, and then we can use FRILO to complement some other connections, like a splice connections, other end connections, or some things that are a bit more simplified here and more flexible than the connection, the component-based method. And we have a lot of data here also. So each component is also checked here, and we have data, we have unity checks, and we have even execution drawings for that connections. And of course, this engineering report can be then integrated in the main SCIA engineering report. So if we feel that SCIA cannot find a solution all the time for our connections, we can also use this FRILO suite, which comes with special application dedicated to check some additional type of connections that are not covered by SCIA, and with the possibility of integrating the results in the main. And now we'll have a look on the star of the show, the structural glass element. We see that although the initial 3D model was done with 1D members, to check the capacity of the glass, the worst facade and the most stress area identified in the 3D model can be checked using a shell model. So you see that each of the laminated glass elements is modeled as 2D shells with equivalent thicknesses depending on the laminated glass package. And these thicknesses are calculated by the software based on the user input. So you have some 2D data that you attach to these 2D shells. And the main advantage is that we can take into account the stress concentrators. So you see here that we have all the spider connections, we have the openings modeled, the soft materials between the bolt and the glass itself, and we are able to see unity checks directly. Because when designing glass, we are not only interested in the biggest bending moment, we want also to see what happens around the stress concentrators in the contact between the steel or aluminum plates and the glass element. And everything is integrated as well. So as you've seen, we didn't let SCIA to make this kind of calculation. The report is very transparent to be able to be compared with a hand calculation or any consultant or checker to also sign our results. And with glass, we also covered non-structural glass, like the insulated glass panels. It can be double or triple insulated glass, and the software will calculate the load sharing distribution, and it will also calculate the isochoric pressure. So this kind of data is a bit outside of the scope of Eurocodes, and EN 16112 covers this and describes, and this is valid in over 50 countries, this code. So the code is integrated into SCIA. You just provide some additional data required for the elements that we design, like the composition of the insulated glass unit, the location in order to calculate the isochoric pressure, and also we can say which loads we applied so that the software calculates for us automatically the load distribution that gets applied on the multiple panels. So this is the result of this module with the insulated glass units. We see here the coefficient that get distributed between the glass panes that built this insulated glass unit, and even the pressure on the unit is displayed here. And everything you see, it can be included, embedded in the engineering report. Now, after we finish the design, we need to return to the detailing software, and we can jump to SDS2, which is part for some years now on the Allplan family. The communication can be done with SAF, is the most elegant, because SAF is a very easy to control file. It's actually an Excel-based format, we import the SAF file, there's some recognition that needs to be done between the SCIA profiles and the profiles from SDS2. It's no big deal. And then we'll get automatic rect members, because SCIA works exactly like a steel detailing software as it is with SDS2. And the members are recognized from material, cross-section point of view, and analysis axis. And the strong point of SDS2 is the automatic connection possibilities, or a database of connections. So actually each member has properties that describe the endings. So the start of a bar and the end of the bar can be controlled by a connection type, which can be auto standard or a user defined or some typical designs. So we have the possibility of getting some automatic connection for simple shear connections, or we can model ourselves more complex solutions and get automatic numbering of parts. They are called material and submaterial, but they're actually assemblies and parts. So this level is accessible, and the main advantage is that we did not need to rework the project. We just use SAF import to get everything in place. The connections can be recognized based on properties, and in case we don't get an automatic connection that we like, we can jump in and force it and arrange it to have a proper result. Now, if we jump to execution drawings, this is something that was required. You see, although it's a very small building, it's very complex. What you see here in these plans are some fountains that cover the art gallery. So there's water flowing and changing colors and dancing and so on. So it was quite difficult for formwork detailing and for reinforcement to transfer this into 2D. Of course, we deliver plans, and Allplan is excellent for this. We try to make as many sections as required, but in the end, the 3D model shared through a common data environment proved a lot of value. So the drawings can look like traditional drawings. The main advantage is that we have the automatic bending schedule. So let's focus now on the workflow. The reinforcement that has been calculated in SCIA can be transferred via ASF files. That is for 2D members, while for 1D members, such as columns and beams, we can actually transfer the reinforcement gauge via IFC. And let's see exactly how this works. So we can isolate these two slabs. There's also a joint that we inherited from the underground parking. We can look at the slabs, and we define some templates, like we choose the quality of reinforcement steel and a recipe. So what you see with green, with blue, it's the typical main reinforcement, and with green, we give it the possibility of adding additional reinforcement exactly where it's required. So this is an approach which shows graphically where are concentrations of forces and where we need to provide additional detailing because of some concentration. It's based on the local system of coordinates, so it actually converts into bar diameters, or we can see area of required steel. We get an engineering report that justified this calculation. Even the detailing provisions are checked within SCIA, so we get a lot of data if we want to see very detailed data that justifies and makes some warnings. Because of the concentration of forces, it's actually better to reinforce in Allplan. So we get all this ASF data that we just exported. The IFC should be at the same coordinate, that's one condition. And then we can start reinforcing realistically in Allplans, and this can be done by a draftsman. So an engineer maybe calculated the required reinforcement, just shares the ASF file, and the engineer, the draftsman or the engineer who's doing the detailing just provides natural Allplan functions. So he can use automatic detection of contour, just specifies here a concrete cover, and clicks, it identifies automatically the polygon, the thickness is read automatically, and we can also say where we want the concrete cover, on the lower side or on the top side. We choose a bar diameter, and also the bending shape, the anchorage, to be according to code and to our practical requirements. And as you see on the right side, we see the requirement that the color changed to white when we provided enough reinforcement. So it's a very interactive way without the structure analysis engineer giving too much sketches and explanations what the draftsman should do with those colored parts. So the draftsman just knows detailing rules and starts reinforcing until it gets white, of course, with the final approval from the one who did the calculation. But in the end, you have here the zones that require more reinforcement, and they were interactively done here. And it's in 3D. You see, even if it's simple building, it's small building, the detailing, it's not simple because it was very difficult because it was built on something existing. But this is the level of detailing you get for the bending schedule. So each bar is automatically mentioned in the schedule, as we can see here. And these are the drawings. So there's a layout manager, which helps us build our layouts that are going to be sent. It can be color coded, the reinforcement based on steel quality or marks and so on. So the traditional is here, but it is actually interactive. So we can jump in anytime and have a look in the 3D model, and it's easy to check. So you see here how it looks on the right side. It's actually how we look on site. I actually have some pictures prepared for you. It's very easy for draftsman to understand the bar and not to mess with reinforcement, especially of the color coding of the bars. But on site, things can get more complicated because the bars are not painted on site. Of course, we need to have enough friction between the reinforcement steel and the concrete. So we'll jump to project management part, which was actually the solution that helped us communicate even better. So because as any project, we were in a rush, we did not make any compromise with 3D reinforcement or the detailing, but still, if you have a look at this picture, it's quite complicated to detail exactly the variable bars that should be placed, the marks and so on, even if we give them with colors on the drawing. So in the end, we used the common data environment called BIMPlus, which required no effort from the contractor point of view, although he wasn't using such thing before. We just invited him to the platform, and using his own laptop, he could jump in and check his bars and check all the data correlated with the plans. So the idea was that the reinforcement was produced according to bending schedule. We had reports, automatic reports from Allplan for that. And then he just needed to identify where the marks are. So every time he didn't find a plan or a certain detail or wasn't sure of something, he would just navigate and click on those bars. And let's see exactly how this looks, this BIM platform. So actually you don't need to install it on anything. It's just browser based. You just go on your favorite browser and you connect to this account. The customer doesn't need to have any kind of license. You as designer have a license for this, and you just invite him to your project. And it's also a common data environment, meaning that here we centralize all the drawings for production, building permits, and so on. So it's more than a viewer of 3D. It can also have approval workflows, and also it can have IDS imported here. So exactly for BIM manager is something that can be used to control. So you can get the IFCs from various software, as I mentioned before, different models, and you can use them to overlap them, see changes, track, and so on. So we'll have a look on the viewer part of it. So it's more than just looking at the 3D model. You can control the content. So you can see maybe the reinforcement is of interest, and we want to see quickly which bars we need to position. You see here position 23. We have 50 bars of 10 at 200, and we got here before we start looking in the PDFs for the proper name. Even the bar is textures and so on. And there's also no effort from the engineer who delivered this. So he was just working in 3D as I shown before, and just shared this data with the contractor. The contractor, although it was his first time, he was very happy to find any kind of bar and without calling us that much and getting things done correctly. And also he was very happy that there was no additional bars that needed to be adjusted on site because everything was done properly and was transferred properly. So this integration allowed to insert the data also from the SDS2 part, so from the steel platform, so everything could be seen here, and also moves very fast. You don't need a strong computer because the data is processed on cloud computers, which are very powerful. So this kind of data doesn't limit you to a computer. You can actually access it from any kind of mobile platform. What I'm showing here is that it can also schedule simulations, so you can connect with Microsoft Project. This is the part of the project manager. He can make some stages of construction and connect those stages of construction with the data from BIMPlus. You see here, these are the stages: infrastructure, steel structure, and so on. You just add this data to that specific stage, and then you can make like a simulation, a time-dependent simulation, a 4D model, and get more data. So everything is just there, but it's important for the one who's responsible with it and to who knows the deadlines and follows and wants to update or wants to pour this plate, for instance, instantly he gets results of the formwork needed, concrete that needs to be ordered, the quality of concrete. So it's a very easy way of accessing all this smart data, which is there by default, by the way the BIM authoring tool created it, or any third or any other software like SCIA provided and SDS2 and so on. So all these attributes can be read with this platform. And as I said, it doesn't limit to browser, to computer. You can quickly make this kind of checks and make notifications and make tasks, get data for a certain model from the pocket. You just grab your phone and you get a lot of data instantly. Imagine on site, it's sometimes difficult to open a laptop, and this data is connected in cloud. So as long as you have an internet connection, everything works fine. And even on tablets, you have even more flexibility to make notes and transfer data directly to the designer. So this provides a lot of value, as you can also make pictures on site, localize problems, and have a very good communication even before you have the actual plans. So the plans can also be linked to elements and accessed in this platform. And it's just about convincing the contractor to work with something that is already there, made by the designer. And now, in the end, I just want to have take a quick look at the challenges that the construction as it went, so from the initial state to the final state. But to make sure that I'll keep you interested, I'll show you just a quick recent movie from one organization that promotes Oradea city. Oradea is the western part of Romania. It's a very nice Art Nouveau style city, and this glass building is positioned in front of the city hall, between the synagogue and the city hall, and it's in kilometer 0 of Oradea. It's a main attraction, and there's a 4-story underground parking there. So it also has a role, this building. So it has a functional role. People leave their cars, and it's near the river bank. So it's also challenging not to have any infiltration. So it started with this nice city. This is I made when I went to a phase to see the reinforcement. This is how it looked from the plane. It's my phone picture, and this is already the reinforcement. So just I position it here to see that in reality it's a bit rust, it's brown, it doesn't have the color coding that we saw in Allplan. However, you just grab the phone and you see it colored, so it's easy to check and see marks there. So just some small details. These are some chemical anchors because they needed to make the anchorage in the existing walls of the parking, and we made some unfolding of concrete to insert the chemical anchors. This is drone footage, drone pictures of the complex reinforcement. So it's not big, but it's complex because everything is variable. And with this detailed schedule that we got from Allplan, there wasn't anything not fitting. This was a temporary stage. There's also a small bar here that I wanted to show because it was on the same concept, meaning that it was hidden in the bars and no columns were in the visible. So it was hidden exactly in the desk, the reception desk of the bar. So this was near it, and this is how initially it looked. So it didn't look that nice, and I want to point out with this picture how would it have looked if we only had steel and concrete. So it was a shame to keep this black steel hall looking like structure in front of such a marvelous building. So the glass here was being installed. So we see here one of the guys installing the panels. There's a spider system that is connecting the glass columns, the fins with the panels, and it was a nice looking phase. So everybody was nervous. Why glass? Will glass maintain? How can you make a glass column? But we actually did. So for Romania, it was quite a remarkable project. These are from initial stages, so there's also some steel structure holding the rocks, this finishing of the building, and this is almost done. They didn't install yet here. They were just the Art Nouveau steel was just for architecture and aesthetic reason used. And this is how it looks during night. We can have here a preview of the lights that are projected on the building. And luckily, this was also nominated in SCIA. It was appreciated by the public. It was nominated, did not win its category. However, it was an honor to be somehow part of this project and see my country here listed. So Terrif Prod is the design office, the engineering office I want to say a few words about, and they did this. I only assisted them with the glass part and my expertise in this field. So it's a company established in 1994, but you couldn't have a company before 1989. So the main player here, the father who has two children, he used to be a coordinator in an institute of design, and then he opened his own family and he worked with his children, engineers, and they worked together as a small family. And with the power of this solution that I presented, they managed to do impressive project. This was just one of them, and they were always pioneers of BIM, pioneers of glass design, pioneers of BIM integration, and so on. So they delivered many successful projects throughout the years, and this is one of them. This is the daughter of Mr. Adrian Muntenaș. She's Ioana Muntenaș, and she was the engineer who made the calculation. And the project was delivered to Oradea municipality. These are the building owner. The main architect was Alexandra Buxuc, and the contractor was Construcții Bihoresa. It's a big contractor from the area. It took some time to build it, but I think the end result was very nice. And we already got here to the question part. So if there are any questions, I'll be happy to answer. Yeah, I hope it was interesting, and I already exceeded a bit the webinar. So if there are any questions, I'm very happy to answer now. Any kind of question, it can be from the engineering, because I was next to them, I was on site, I followed this work, but also related to software. I'm more than happy to answer if you have any kind of questions. So if there are no pressing questions, I thank you for your attention. Here is our contact data, mine and Tac Chabon, the contact details. We're happy to follow up with more details and answer questions. Maybe if you watch carefully the recording, there might be some question regarding what we presented. But I can only say thank you and enjoy the rest of the day, and hope to see you on other events organized by SCIA. Goodbye, everyone.